Okay, let's meet the groups of echinoderms. So here we've got Helicoplacus, which remember has that Y-shaped groove. So here it is wrapping around, and this is going to wrap all the way around the back and come all the way down to here. And there it is, it's splitting on this side, and then these are going to wrap around, and they would almost come around to here on there. So it's not quite helical symmetry, although it's trying. It's definitely not bilateral symmetry. It's real weird symmetry. There aren't very many things that are built like this. The one thing that's kind of close is a helicocystis, which looks like a little tiny crinoid stalk and holdfast and cup. And then it's got something like a helicoplacus on top. But instead of having, so presumably the mouth is right here where the ambulacral grooves come together, although it is hard to see and these are not well known. This one does have a mouth with actual potential mouth parts that could come together, like the biting teeth you would find on an echinoid. Anus is all the way down here, tucked between a couple of the arms, because why not? And what you may have here is something like an edrioasteroid, which are very flat, but that's doing ecological tearing. So it's an edrioasteroid that's sort of pulled itself up into a kind of a teardrop shape, but is still basically working the same way. That is an explanation. I don't know. I don't know what else to do with that. And there are some other fossils from the lower to mid Cambrian that don't really fit with any of these things. Camptostroma, I think, is the name of one of those. All right. Here are tenocystoids, which I just find delightful. These are the proper tenocystoids over here. And you can see they're trying their hardest to have bilateral symmetry. This one, Cortisolia, it's so tantalizingly close to being bilateral. You could fold it and it would almost line up, except that every single plate is a little bit different from every single other plate, and it's just not. Um, and here is actual Tenocystis, and these are close, but look, they have an extra plate that's kind of off to the side. So really, that's just the central plate, and so here they're marking similar plates in similar colors. And what you've got here, this is like the underside of it, and this is the top side of it, underside, top side, unless we have that backwards. And this is actually the top side, and that's the underside. I am not sure. I'm not sure if anyone is sure, but there are probably people with opinions. Yeah. Here is a syncton. So you can see a syncton is basically a tenocystoid with a sort of a mobile tail for propulsion. Here is something that's kind of halfway in between, Tino imbricata. So this has almost bilateral symmetry. Pretty good imitation of bilateral symmetry. It's starting to elongate, and it still has the sort of anus down here, which you get on Cortisolia. But the idea is that this is on the way to becoming something more like a syncton. Yeah. So who knows? Here's another tenocystoid, and this is just here to show you this is the way that each of these plates can move. So each of these, the comb apparatus, they're like little fingers, and we don't know if they could move together or if they could have some of them up and some of them down. And are these pulling the organism along while pulling dirt into the mouth of the organism? Presumably the mouth is right behind here. Great question, hard to answer. Where is the anus? Maybe down there, but not even certainly. Or is it coming out the back? They have a little stub back here, which is like the start of a that sort of propulsion limb that would come out the back. So maybe. Okay, here's a syncton. So they've got propulsion down. Bam! They've got that back arm. The arm is not for feeding. The arm has no ambulacra on it. It is there for eating. If there is an ambulacral groove, it would run right here. It'd be sort of twofold-ish symmetric with one long one and one short one. And these tube feet will be pumping stuff into the mouth right there. So yeah, you get your plates around the mouth. And these would be the 2, 1, 2 of that famous law. And so the idea is that as it goes along, it's going to run into things it can eat, and it's going to pop those into its mouth and carry on. All right, here's another attempt to put a few of these other things onto a tree. So this is mainly looking at Tenocystoids. So Tenoimbricata down here. That being a little more closer to Cinctons because they're going to share a direct common ancestor with regular Tenocystids being a kind of like an evolved branch off of this. And then all the ones that you know and love are way up here. All these early branches are gone. Yeah. It is other newer versions of echinoderms that have completely taken over. All right. So, cornutes. What are these things? And we've got a fossil, and it has these two on it. They're together. Oh my gosh. Yeah. Look at this. So this is what I was talking about. This is that thing that's kind of like a gill. And so presumably that's going to be on the top so it can vent out, which would mean that these with these sort of bigger plates are going to be on the bottom. The littler plates would be on the top. And so here, once again, you have this sort of gills down here at the back. The mouth, I believe, it's either here or down at the bottom of this groove. These things are always found basically flat, just as like molds of extremely thin, flat things. Somebody must have found something, but they do have an. Actually, I think that's the anus there, and I think the mouth is somewhere along here, and I think these are just sort of passive channels to push food in toward the mouth, which I would imagine would be somewhere right about there. But yeah, I am not sure. These are really weird. But they do have that one large limb for propulsion. And so they're going to be moving away from this limb. They're going to be pushing along. And basically, yeah, they're going to snowplow that dirt with these sort of static arms right here. It's just going to channel the dirt in toward the point where it actually wants to eat. And it wouldn't have much control over what it's eating unless it had some sort of taste receptors up here and some ability to control its motion from the tail. But it could just about work. And they did really well. There are lots of fossils of these things. So, yeah. All right, here are some of the more complete fossil cornutes that are out there. So here we can actually see some of the parts on there. So there's an anus, and on this one it's located up on top. That's neat. This thing, which is kind of like a gill, which is maybe a vent for the water vascular system, maybe, is down here. We don't actually know what it is. I guess it could be something like a gill. These things lived in hypoxic environments, so very low oxygen, fairly deep water, and so they may have needed some sort of additional machinery to be able to gather enough oxygen to be able to exist. Yeah, it's possible. The mouth would presumably be somewhere along here, and I think they don't ever annotate it because it's difficult to be sure exactly where it is. Okay. Here's a mitrate. Now this is a mitrate with no arms, and most of the mitrates you'll see will have 2 arms. They look like little devil horns on the top. It's going to have, mouth plates right here. Great big plates covering all over. It's got paired openings at the back. And so we're not sure if these are openings, like one of these is an anus and one of these is for the water vascular system, or if they're both doing both, they're somehow channeling into this. No idea what's going on internally with the soft parts of these. It will be great when somebody finds some of these and is able to kind of fill in the missing soft parts on them. But yeah, the mouth is up there, and so presumably they're propelling themselves along via this organ at the end, and just sort of scooping and eating whatever they need, whatever's coming in front of them, and then the waste is going back out the back. Yeah. These are called eyes. That is one possible interpretation of what they could be, but from the look of it, they would be on the bottom. So I think that they're more likely the water vascular system, sort of paired openings, and paired openings for the anus. Those would be my guess, but I am not an expert on these, so do not take that one at face value. Okay, solutes. Solutes are going to have an arm for propulsion and a separate arm on the top for eating. So they're going to grab food here. Not actually doing that. They're going to have an ambulacral groove running along this arm. And so this is the first time we've kind of moved. So if there's an ambulacra here, it's running along the edge of the shell, maybe in between the plates, maybe on top of the plates. But it's real cryptic. Same thing down here. If they have ambulacra, they are really hard to find. Like, could it be in these two grooves? Maybe, but are there the expected features? No. So, if anything, ambulacra don't ever really develop, or they're developed on these guys, definitely. And we see them again here. And we've actually moved the ambulacra off the body for maybe the first time. So the idea is that solutes are extending the ambulacra to get more reach on feeding. And so this would be advantageous in a situation where you're trying to do ecological tiering, where you're trying to get a little higher in the water column to feed up there. But as far as we know, these things were on the ground and they were still crawling along. It may be that some of these could do both. Like they could move when they needed to move and they could then stand upright to feed. Very possible. Yeah. Enigmatic little creatures. And of course, when they're dead, they would all fall down. You wouldn't ever get them preserved, like standing on their little tiny tail. So, yeah, it's just not known. Just not known. Here is an awesome old picture from the treatise of Rhombifera. These are going to have nice ambulacral grooves, but they're going to be back on the body now. And so maybe don't think of this as back on the body. Maybe think of this as a branch that hasn't moved them off the body yet. There's like, we're going to keep them. Grooves are going to be on the body, and we'll grow little arms on either side of the groove to help feed. But the actual ambulacra will stay on the body. Here is a rhombiferan's mouth, and here you can see the kind of weird 2, 1, and 2 symmetry, if I'm reading that correctly. I think that's right. Oral 1, so 2 and 3 would be a pair, and 4 and 5 would be a pair. And those are the first oral plates and the second oral plate. So they'll grow special plates around their mouths. In sea urchins, these plates are actually mobile. There's muscles, and so they're going to scissor in toward the middle. And you'll have 5 of these little biting plates coming together. They are awesome at scraping stuff off of rocks. And they keep growing, if I remember right, so that as they get ground down through use, they're going to keep getting replenished from the inside. This is what, if you ever see somebody that's cracked open a sand dollar or something like that, these are the little things in the center. They call it like a little lantern, but it's just the little teeth that are there that are together. Okay. In addition to crinoids, which are a specialized version of a rhombiferan, and they have their arms that are up in the air, so maybe they're more like solutes. We're going to have, I think, 2 separate entire lectures just on crinoids, so we'll just chill on them for a minute. But we got to mention blastoids. And so blastoids are a particular type of rhombiferan. They almost have 5-fold symmetry, although it's definitely closer to twofold symmetry. They've got a little anus up here. You can spot it because it's the one little hole on top that is larger than the other. The mouth is going to be at the center. Here are the 5 ambulacral grooves. And there used to be little tiny brachioles, like little feeding arms that would stick up off of the edges of both of these. So you can see the little attachment points. The body, the calyx, whatever you want to call it, of this one, and it was stalked uh, like a crinoid. The calyx is usually very well put together, like pretty well cemented together. They're generally found intact, whereas the columnar segments will just sort of shatter and scatter. But yeah, blastoids, they're made for fossilization. These things do well, or did well, in low energy environments. So in lagoons where there's like a reef out here that's breaking all the waves. And so you just get like nutrients washing over and into the very calm lagoon. And they would just hoover those nutrients up, basically. Yeah. Okay, here's a person attempting, to put all of this together, and I respect the attempt. So the idea is that, okay, we're going to start out, big brain, with bilateral symmetry. Okay, so one of these tenocystoid guys with proper, almost-ish bilateral symmetry, because all the other branches that come off of the early deuterostomes do appear to have bilateral symmetry. So makes a lot of sense for the early ones to be symmetrical. Then it goes through an asymmetric phase. You got your synctons here, you got your solute here. It's going to go through a sort of a triradial stage. We got to put Helicoplacus in here somewhere. It doesn't really fit anywhere. But it is mid to late Cambrian, if I remember right. So it doesn't have to be the earliest version. Helicocystis is there, which is like our big puffed up version of an Edrioasteroid. Camptostroma is also it's like a medium puffed up Edrioasteroid, although people do disagree on exactly what this is. And then you start to get your rhombifera, you start to get your eocrinoids, which may not go on to become regular crinoids. They may actually come off of this branch over here. And stromatocystis, good luck with that. It's a weirdo. Maybe that's the one that turns into Edrioasteroids. I think they're more like Camptostroma, though. All right. Ooh, yeah, we're almost there. We've got to look at this little bit of development, and then we've got just like a little quiz yourself section where we'll show you some fossils and see if you can identify what group they belong to of the many, 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 many groups of early echinoderms. Because they're fascinating. And at some point, somebody's going to be able to put all these pieces together. I believe in that. And that's going to be great. All this is going to make sense, and it's an awesome story. It's just that it is not fully assembled yet. Yeah, we're still getting there. So, during development, you have your little baby, and so on the inside, you're going to have this empty space. That's going to be the coelom, and that's going to turn into like a gut in humans, for example. The coelom in echinoderms is actually going to be divided into multiple coeloms. And so in most of these organisms, they're going to call it the right and left somatocele, and then the one that would have been further to the left is going to be the hydrocele, which is going to become part of the water vascular system that runs the tube feet, if I remember right. These are going to persist through life, and so usually the right somatocele is going to be bigger, and that's except in echinoids, in things like a sea urchin, and there is the left that is just dominant, that is doing most of the work. Yeah. All right. So, let's look at these. Now, pretend the names aren't there, but let's look at these. So what do you see? I see 2 tenocystoids. Here and here, right? Almost bilaterally symmetric. Got a little anus on there somewhere. Got this comb-like organ at the front. They're just cool looking. Yeah, I think they're pretty recognizable. we've got Gaugia, and Gaugia is going to be an eocrinoid, and Gaugia spiralis, I think, usually has 5 arms that are each divided into 2, so it's like 10 little mini arms, but they come in pairs. Yeah, like that. So that is an eocrinoid. This is a definite syncton, absolutely. So there are other fancy terms for these. Forget homostelia. Yeah, just, that's fine, but we don't need to learn that. So let's think of this as a syncton. We're going to go with the sort of common name-ish thing. Forget stylophore is the name for the appendage, the movement limb. And so they are in the stylophore, but these classes are dependent on how you see evolution. And since the evolution is not very well pinned down, we're going to pretend that some of the higher taxonomy is not there until it is fully sorted out, and then we'll bring it back in, in future years of the class. But this would be a mitrate with the big plates here, and paired openings at the back. All right, what do you see here? I see some beautiful, so it's saying blastozoans, but these are going to be basically rhombifera. And so here you got ambulacral grooves on the edge with the little tiny brachioles running off of that, looking great. And some of these things are so weird. A few of them will have 5-fold symmetry. So this is maybe on the way to becoming something like a blastoid. But it doesn't look like a full blastoid yet. I'm not going to put something like this on the spots test because this looks transitional to me. Something like this can really only be a rhombifera, and so that's a fairer thing, I think. All right, up at the top we have, that's the word they're using, but these are basically like edrioasteroids. I think of them as being on that branch, and there are some papers that would classify them that way. You've got tenocystoids here, looking great. You've got some rhombiferans of some sort. Looks like that is a syncton, but we're missing some parts of it. That looks like an eocrinoid down there. Yep, that's fine. And then this is all twisted, so this has got to be a helicoplacus-like form, or helicocystis, based on having these little extra plates down here. So that would be a difficult one because we can't see all of the organism. But helicoplacus, helicocystis, I think either of those would have to be acceptable in terms of an answer. These, finally, are very much easier. So we got our tenocystoid, we got our syncton, we got our helicoplacoid, we got our eocrinoid. That's about as solute as you are ever going to see. And then this would be an edrioasteroid. And stromatocystis is a kind of thing that, I would say probably is most visually similar to edrioasteroids and the potential precursor to them. All right. Some of the same things as before. That's fine. Don't be fooled. It makes it easy. So we've got our eocrinoid. Look at those nice round plates here, a little base where it's going to be anchored onto the ground. And we've got these long, luscious feeding arms. Look at those. They look great. Here, it looks like we have some, let's see. Let's go back. Let's go back and see who those are. We have a cornute? I think we do. I think that's who we've got. Although this one looks like a syncton. Let's see. So C is a syncton, because it's got the big plates around the edge and the tail for mobility. And B is another stylophoran. So, I don't know. I guess you could put that in with the cincta. Not sure. Let's see. Here's a nice little rhombiferan down here. As I would say is this, as is this. It's just sort of crushed. I think they're calling it an eocrinoid, but I don't like the term eocrinoid. This is an edrioasteroid for sure, and then this would be that thing which is closest to edrioasteroids. But I'll show you some of the examples from the collection. That's what we'll be taking these from. And that simplifies it, I think, a lot. Yeah, narrowing it down to just those few. So, boy, was that a lot of names. Go back, look at the names, memorize the names, get a couple of pictures of each of the things that the name is about, and then I think you'll be able to do this. This one's going to take some flashcards. We got to learn our early echinoderms, and who knows, maybe it's going to be you that ends up putting these things together in some kind of order that actually makes sense in terms of when the fossils are found and makes some sort of genetic sense. Yeah, I would love to see it, whether it's you or anybody else. All right. Thanks very much. This one's going to take some studying, but I believe in you. Go for it.